So now that we see that homomorphisms are sort of ubiquitous in groups, in group theory, we want to sort of see what can we learn about them. Is there any way to sort of measure any additional good properties a random homomorphism might have? The answer is yes. There's a couple ways to do that, and the best way to do that is what kernels are for. So we're going to, in this handout, define what a kernel is and give some of its basic properties. I do want to point out that if you open up your linear algebra textbook, you will also see kernels. In that class, you took the kernel of a linear transformation of vector spaces. And this is exactly the same idea for groups, which is why it's still called a kernel. Okay? So it's actually very, very, very similar. You'll even see some of the same theorems. Okay? So here's the definition. Suppose that I hand you a homomorphism alpha that goes from G to L. Okay, the kernel of alpha, denoted by Ker alpha, is the set of all points in G, the set of all elements here, that happen to map to the identity in L after you apply alpha. Okay, so it's all the x's in G that satisfy alpha of x is equal to the identity. Okay, so here it is written as a set. Okay, now at the outset, the kernel of alpha is a subset of G, right? It is a collection of elements from G, so it is a subset of G. In this handout, we're going to prove that's actually a bit more. It's actually a subgroup. But from the definition of the kernel, it is very easy to test whether or not any element X in the group G happens to live in the kernel of alpha. It's very easy to check it. You simply check whether or not this condition holds. You just plug it into your function alpha, and you check whether or not alpha of x is equal to the identity in L. That's all you do. So it's never hard to check if a particular element lives in the kernel of your homomorphism alpha. Okay? So let's prove the first proposition, which is suppose you had alpha from G to L, and that was any good old homomorphism. The claim is that the kernel of alpha is always a normal subgroup of G. Okay. Now I'm only going to go through the first part of the proof here. You should read the rest, but I'm just going to use the subgroup test, and then I'm going to check normality by conjugates. That's what happens down here. Okay. Now notice that we've already proven that alpha of the identity in G has to be the identity of L. So there you go. There's an element that has to live in the kernel. Right? So no matter what your homomorphism is from G to L, the identity in the domain group has to be in the kernel. We proved that last time. And so the kernel is always not empty. And so I'm not going to run into this issue with subgroups because the kernel we know is now not empty. Okay? So to make the exposition easier to follow, instead of writing Ker alpha a million times, let me just call it big K for right now. And so I've already argued that the kernel is not empty, so I can proceed with the definition of a subgroup here. So suppose you take two things from this supposed subgroup. I want to show it's a subgroup, so you're supposed to take two things from it and show that A times B is also from it, right? So if I assume that A and B come from the kernel, that's information, right? That means that they satisfy this property. So alpha of A has to be the identity, and so must alpha of B. My job is to prove that A times B is still in the subgroup, is still in the kernel. But remember, it's easy to check whether or not somebody lives in the kernel. You just plug them into alpha and see if you get back the identity. So my job is to plug AB into alpha and ponder whether or not I get back the identity. But I do, because alpha is a homomorphism. So alpha of AB is alpha A times alpha B. But we just said both those terms were the identity in L. So this is identity times identity, which is, of course, the identity. And so, haha, that is correct. A times B must live in the kernel. And then you do the same thing, and you check that if A is in the kernel, then so is the inverse. But once again, you're going to be saved because of properties of the homomorphism alpha. So it works out. And then finally, that proves that this is a subgroup, but it does not prove normality. And so to prove normality, you got to prove that K is closed under all conjugations from G, and you can read the proof of that. It's a straightforward calculation. So what you end up with is the true statement that, yes, kernels are always normal subgroups. Okay? So I'll leave you here with two examples. Look back at example 4 from the previous handout. In that case, let's just do a special case where we work mod 3. In example 4, we were working mod n, but let's just work mod 3. So in that case, we have the homomorphism alpha, which maps the group of integers to z mod 3 by sending any integer x to its congruence class mod 3. Okay, so 2 would go to class 2, 4 would go to class 4, which is class 1, 9 would go to class 9, which is also class 0. So that's the definition of alpha. What's the kernel of alpha? Well, just read the definition. By definition, an integer z from z would belong to the kernel of alpha if and only if alpha of x were the identity in z mod 3, but the identity in z mod 3 is class 0. So that would say that x belongs to the kernel if and only if the class of x is the class of 0. All right, so there we go. X is in the kernel of alpha if and only if the class of x is the class of 0. But class of x is the class of 0 if and only if x is congruent to 0 mod 3. Well, who's congruent to 0 mod 3? That's just all the multiples of 3, and that's the subgroup 3z, the subgroup generated by 3. Hence, the kernel of alpha must be that subgroup 3z, and notice, of course, 3z is a normal subgroup of z, so everything seems to be working here. Okay. A really nice example of this is example 7 from the prior handout. There I gave you this piecewise. Here's a piecewise homomorphism that goes from D4 to R star, the multiplicative group of the non-zero real numbers. Here you let alpha of x be 1 if you plug in a rotation, and let it be negative 1 if you plug in a reflection. So what's the kernel of this homomorphism? Well, the identity in this group R star is 1. So you're asking, who is it in here that maps to 1? Who maps to 1? Well, the rotations do, right? So here we see that the kernel of alpha is all the rotations. So the kernel of alpha is just the rotation subgroup, right? Now look, we just proved that kernels are always normal subgroups, and look, here you go. This is, notice, a normal subgroup of D4. We've already proved that. It's a subgroup of index 2, okay? So we're coming full circle here a little bit. So finally, let me leave you with probably the most important application of homomorphisms and kernels, okay? Here is a handy-dandy way to tell if a homomorphism that you're handed is one-to-one, okay? This is actually, by the way, the same theorem you have in linear algebra. You learn that a linear transformation is one-to-one if and only if the kernel is trivial, the trivial subspace. And here we have exactly the same theory in group theory. Suppose that alpha from G to L is a homomorphism of groups. Then alpha is one-to-one if and only if the kernel is the trivial subgroup of G. Okay? And I walk you through the proof here. The proof is not hard, and I'm very explicit. I lay everything out. So read this out and make sure you understand exactly why this is true. Okay? But there's an easy test to tell if your homomorphism alpha is one-to-one. You simply check whether or not the kernel is the trivial subgroup of G. Okay? Now, at the end of this handout, I give a slight extension of this theorem that deals with cosets of the kernel. And this is kind of a fun discussion. So, to be honest, we're not going to need this part this much this semester, but we will in the fall. So when it comes time in the fall in Math 432 where we need this, I'll come back and I'll redo this all over again. But there's no reason you couldn't understand it right now. But this sort of tells you something about not just what the kernel has to do with your one-to-one homomorphisms, but also what it gets into is what the kernel might tell you about cosets and what that says about your homomorphism. So this is kind of an extension of Proposition 2. So you can read this and see if you can follow. It's kind of a neat fact. So try this out. If you get stuck on any of these facts and theorems, let me know. Your next graded homework set will probably relate to all this stuff with kernels and homomorphism. So read this and let me know if you have any questions.